Swayam Prabha. Digital India. Educated India.
So I am very happy to be here. It won't be a lot of notes taking lecture, so don't worry about it. So I have put it like this: mostly optics and spectroscopy, also electromagnetism. These are some of the photographs which you don't have to worry, but that's how you see in the lab when you do experimental physics in optics and spectroscopy. This is the kind of photographs you come across. This is me there, and you know where it is. Anybody here? Anybody knows who? Anybody don't know where it is? Just raise your hands. Yeah. Anyone else? Yeah, it doesn't have to worry about it because your tour will go. I guess the organizer should take you there, so you should see. More importantly, just imagine that this is on the Mars. Then you would like to know, I mean, forget about that part, the pressing part, but you would like to know what is the constituent of this stone or this rock. That will also tell you that what are the things in Mars, whether they are expensive, they are useful, whether it is worth going there and, in about for 2 years flying to go to Mars and then 2 years coming back from Mars, bringing something useful. How do you find out from here before you go? Right? That's the kind of question. So you could take a spectrum of that stone by either directly by the sunlight, or you could also take spectrum by ablating it, let's say melting it or evaporating it so that some ions or some elements come out in those fourth state of matter, which is known as plasma, and then see what are the lines corresponding. Remember the hydrogen atom lines from the sun, the Balmer lines and Paschen lines and so on. That's how you know sun has those elements. Similarly, you can have the idea of the elements of the Mars surface with this, and for that there are some these Curiosity rover. Do you know that? It's already there. There's another rover has been put recently. Yeah, those contain small items. So there will be one spectrometer which will record the spectrum so that the lines can be identified, because lines are well known. That's what the spectroscopists do in our, those research scholars with big birds with these slippers walking around here and there in those labs. They're only measuring those elements which are known. So the lines, for example, these are tube lights or LED lights? Did anyone had tube lights still at home? Yeah, that 40-watt tube light, no, with choke. Yeah. What is that light? That is mercury light. Sometimes they say mercury light. No? Tube light? Yeah, so that's the gas. What is the gas inside? It's mercury, not argon. So mercury means it's gas, mercury lamp. So it's known as mercury lamp. Is a well-known lamp, by the way, and it has served all of us for a long period of time. And of course, you also have bulb, right? So these are now LED lamps. So if you take the spectrum of this lamp, this tube light, and of that tube light, you would see difference. This would have the color of visible lesion, right? You disperse through the prism, and that would also have that color because both of them give the white light. In addition to that, what will it have? It will have mercury lines also. Mercury lines. So for example, one of the line is 435.8 nanometers. at room temperature, anywhere in the world or in space, you measure the spectrum of mercury, you will get 435.8 nanometers. So that's the spectral line. There will be one at 3650. So now you know two lines. Now you don't know other lines. So you just take the mercury spectrum, take that spectrum, and you can calibrate. You need 3 points to calibrate, right? So that is how you find out. So similarly, knowing the lines of any element of any, you just name the element. I mean, anywhere in the periodic table, you should be able to, also organic materials and so on. So basically, optics and spectroscopy, experimental, is the mother of all modern science, basically. So in 19th century and 1900 onwards, or even before, it has contributed a lot to the modern development of modern science, whether it is theoretical or experimental. Okay, so just I wanted to mention that. So now it's so much interdisciplinary that it has so many things. Engineering, you have instrumentation, you have theoretical knowledge, because you have to calculate, simulate those lines and so on. Well, this is the acknowledgement. So how many people showed this slide in your lectures? This slide means something like this. First slide generally. Thanks to organizers. Yeah? No, what about the other acknowledgements? Training, research teams, students of, DST funding agencies, all this. Very useless looking slide, right? Very important slide. Suppose you have achieved what you want to achieve in your life at the age of 25 and forget to acknowledge one person, you lose the job completely. Can you imagine something? You struggled through your life, you got a fantastic job, whatever you wanted, and then one day you were presenting something or you wrote something and you forgot to acknowledge one funding agency or one person who had contributed to your somewhere. And that person just bounces back through one of the representations, and then it's unfortunate. You justify, you can keep on justifying, but you did not acknowledge. So copying. So remember, from the childhood we have been told, make a report on birds, make a report on animals. So you just go to Google or something, copy, paste it and put a report and give it to the school. Isn't it, next day, or buy something from there. Hardly we place any acknowledgement to the source we have brought that. So acknowledging the source is so important. Writing the name of the person who you have taken help from is so important. It's a professional honesty. Copying is just no, big no. Okay, if you copy, please tell this from where you have taken. Okay, if someone has helped you, you have to mention that, yes, that person has helped me. Of course, there is your contribution, right? Suppose they make some rover, one person cannot make a rover. It needs computer, it needs mechanical, it needs so many other small electronics and so on and so forth, right? So the whole team has to be. And of course, when you take part in those kinds of projects, you have to also identify what work you did. What was I took part in the rover project. What did you do? Okay, that's the question. Okay, well, in NPTEL lab, it's a very small Kumaon University, till now, or maybe you will hear PhD from Cornell, PhD from somewhere. How come a PhD from a NPTEL laboratory can be at IIT Madras as a professor? Okay, that's also a question. So that probably maybe come out a little later. So what I thought is, we'll talk something about electricity magnetism, which leads to optics. We can talk something about kitchen devices, electromagnetism. We'll talk something optics in a cavity at home, optics and monochromatic intense laser light, and some lasers are not monochromatic. You see, what happens is, you talk of a development, you talk of anything, unless it comes to the kitchen, it's not a development. How many of you made tea in your home? Very good. So some people have not yet made tea. That's the first experiment you do at home. making a cup of tea. It's not irrespective of whether you drink tea or not. Okay. So make a cup of tea and see how many things you need. Right? One glass, one filter, one tea, one water, some this thing, some, if you want some black pepper or some turmeric, or what is that other thing? Adrak wali chai. Well, coffee, let's say coffee. How many people have made coffee or tea or something? Yeah, that's good. So making coffee, tea for yourself is equally important. Also, that's the first experiment at home. You must do it now, today, when you go home for the first opportunity at home, give it to your mom. Okay, so that will be greatest achievement. So another thing what I was saying is, unless the development, see, whenever you start, whenever there is a voting, let's say in Karnataka, now there will be polling in 10th. So in the kitchen, there will be discussion about the parties. I don't like, dislike. So unless the things come back to kitchen, the development is actually not happened to the public. Okay. So now you think that what are the things in kitchen? So kitchen is the least important thing. Now Mama gives food, okay. Right? Or you order from other person nowadays, Zomato or this thing, because I don't like this food, I like only this. Yeah, he's studying, so give it whatever he likes, please give. He or she likes. Okay. All right, so let's see. This is electromagnetic spectrum, which you must have seen somewhere. And you know, the only thing which I wanted to mention here was that, so you have gamma rays, you have X-rays, ultraviolet, infrared, microwave, radio waves. Only thing changing is the frequency. Of course, the wavelength. Now the point is, of course, you know this, X-rays are used for imaging those. But visible region we know because we can see. So there are other regions as well, equally important. There are some ionizing radiations, there are some non-ionizing radiations. So if you keep your mobile phone near your pillow in the night, it's not going to ionize your brain because it is non-ionizing radiation. That's what is working there, irrespective of who says what. Okay. But if you use X-rays, so X-ray, if a doctor says, you immediately, honestly go faithfully take an X-ray and come back. So X-ray is ionizing radiation. Therefore, they take care that what dose they give, but the person who makes the X-rays will have a big metal sheet. He would be somewhere else while you are being X-rayed. He'll push a button. Okay, so generally they would ask, would you mind taking X-ray? Okay. So the idea is that actually everything is electromagnetism, everything is light. Only thing is different is the wavelength and frequency. So if you want to measure the crystal structure, you work in X-rays. If you want to see, you work in visible region. If you have microwave radiation, you have some communication and some other things, you work in the microwave region. So that's so many kind of optics you can have. Geometrical optics, you know. Okay, then you also know ray optics, you know this wave optics, and these are other optics which come into picture as we grow older. So any one of you may be working in one of the optics of one of the specialized field later on, whether it's in company or in academics, it doesn't really matter. So much specified areas they become. That is why these areas become so much interdisciplinary. If you are a physicist, you may be working in biology. You are working as a physicist in a biology department. You may be working in chemistry department. It doesn't really matter. So those electrical engineer working in physics department. So later on, when you grow higher and higher, you have the specialized field, and that would make these boundaries actually exist no more. Okay, so that's what happened. So anyway, we don't have to talk about that. The only thing I just said here was that, for example, I wanted to show this. So anyone knows about this eyes of the owl? Difference between the eyes. The owl can see during the day. It can't, because its eye does not have the specific cells which see intense light. It has the cells which see only dim light. We have both. You can also see a little bit of dim lights. Now the point is the retina of the eye, of our eye or owl's eye, has some protein, retinal protein, okay, and that you have to study. The first event which takes place in your eyes is the photon hits the retina, and then many things happen because it has to recycle, it has to see another photon, it can't see once and that's gone. So those events happen in very fast time scales. So suppose you want to modify your eye, the eye of owl, or the human being wants to modify something, nature, play with the nature, do something different. You need to study what the process is going on, and to study that process it has to be measured. To measure those processes, you need some kind of instrumentation. Okay, let's see if it becomes any. So, and finally you have the photon, and then some emission comes out. But in that case, there is a cycle. Okay, like those cycles of, and this equations which you may be knowing, whether you know or not, I don't know. The first equation is the Coulomb's law, or they say is Gauss's law later. It becomes, that's the Ampere's law, Faraday's law, and this is Ampere's law fixed by, am I wrong somewhere there? That's actually have no name. They said no name here. But this is Ampere's law. This is Faraday's law. And this is Gauss's law. These are four equations for charge density rho and current density J and displacement current density this, epsilon naught dou E by dou T. Yeah, I knew that. So I know that you don't know this. I just brought it, okay, because that's it doesn't mean that I am not going to tell you what is delta. Delta is nothing but del by del x, I cap, for one x. But for y, z, you will have similarly plus y, del y, j in Cartesian coordinates. It's a del operator, or you can say, so you read divergence of E is equal to rho by epsilon naught. The second one is curl of E is equal to minus partial derivative of B with respect to time. The third one is divergence of B is 0. So divergence of B is 0, it curls. Divergence of E is rho by epsilon naught, rho is charge density. Curl of B is given like this, but I want to show them because those are the only equations, that's the base of our optics, where we start with. Of course, you will reach at those equations in the first year of your undergraduate classes, okay. But I just wanted to tell you that, so, but you know the Faraday's law. Faraday's law you know. You don't know yet? 11th standard, 12th standard? You are 10th or 11th or 12th? 11 to 12th, okay. So Faraday's law you will know, because Faraday had the coil and he put the magnet inside and there was a current. So actually, Faraday's law is very much here right now. The electricity, you don't know the Gauss's law. You know the Gauss's law, yeah, that's right. So similarly you will know in, so electrostatics you are there, in magnetostatics you are there, then electrodynamics you start going there. Okay, this Faraday's law and the fourth law, Ampere's law, fixed by that. But you don't, I haven't brought it for just impress you or showing you off, because actually it's a negative point of showing those equations in this lecture. But the idea is that unless I show you these equations, you can't enjoy the next slides. Okay. So what is happening here? The E can be expressed time derivative of B. B is expressed time derivative of E. Okay, so something like this. So B and E are related, and E and B are related, and so on and so forth. When you have the varying time, varying electric fields, when electrostatics, the current is steady or the charge is steady, electrostatics, current is steady, DC current is magnetostatics. But if AC current is going, it's like varying electric fields, right? Now, if you talk of everywhere, there is a varying electric field. Electricity, a bulb everywhere there is, unless there is a DC. That's what is happening. Anyway, what we define here is one C, which they measured actually 3 into 10 power 8 meters per second. They found out from the Ampere's law or Biot-Savart's law and Coulomb's law, those two quantities, epsilon naught and mu naught, they found out that C, that 3 into 10 power 8 meters per second is equal to 1 by under root of this. And that is how they found out, oh my God, this light is an electromagnetic wave. Because finally they have a equation like a sound wave or any wave which comes out from these equations. No, I will not write out, but just tell you that, see, what happens is when a point charge has the electric field lines, how do you see them? If a point charge has a field lines, plus charge, they will go divert away from, right? Similarly, if you have a current, the magnetic field due to the current will rotate around the, so that's the curl and this is the divergence. Okay, so that much is enough. If it generates so much of interest, it's very nice, but I would be blamed to be unnecessarily going into advanced courses. So let me just
Sir,
yes,
you written C dash is equal to C by N, right?
C by N.
Oh, what is N?
N is the refractive index.
Refract.
Yeah. So for air we take as 1, but if you take for glass it will be 1.45 or something. Again, tea cooking. So how many ways of cooking anything? One is firewood, gas, induction, microwave. Okay, so many ways you can cook food: hot plate, induction plate, and so on. Have you cooked anything in firewood till date? Yeah, good. At least if you go to the BISAG-N beach, have you gone to BISAG-N? They will give you this butta, no? What is that? Corn roasted on the firewood, coal wood. Okay, so now if you look at this papadam, and if you remove this is the microwave oven. Many of us may not have seen it. So it's microwave oven, works on the principle of microwave radiation. So microwave radiation is absorbed by the water. Therefore, anything which has water will be cooked because the heat is generated because of the transition of the microwave. Okay, water has strong absorption in microwave region. So if you put your hand, it will be cooked without any testing. That is why there will be safety device that the moment you open the door of the microwave, it stops. But then there is a rotating plate inside a microwave oven so that uniformly the food which contains water can be cooked. You remove that plate. So put the papad inside and now switch on for 10 seconds. You see that the papad which you can eat can be only here and here. Two places. You can see the difference between the color. And you measure the distance in centimeters by your scale. It's about 7 centimeters. And then on the back side of the microwave, you can see that there's a frequency given, 2450 megahertz. And because this is one node, so the wavelength is actually double of this. So you can find out the speed of light by that. Because microwave is also light. So it's the simplest way of measuring speed of light. You can put anything, chocolate or anything.
So the distance between those 2 points, that's our lambda wavelength, right?
Not lambda. So this one, half of lambda. That's why these two are focused. So that is one small experiment which you can do definitely. The second thing which also I wanted to mention was that induction cooking, where you have this if you take the cooker nowadays, new cookers, and see on the back of that, you would have this kind of design. The old cookers will not have. And if you take that magnet on the refrigerator, no, you have put some magnets and something for some photograph or something, and you will see that this is ferromagnetic material. The whole thing is stainless steel or something else, but the bottom of the cooker is a ferromagnet. So it can attract the magnet and so on. So now that's what happens. So you have a microwave oven, so which has AC electricity, which has a coils. It generates magnetic field because changing electric field can generate the magnetic field. The magnetic field now can induce the currents in the ferromagnet, some eddy currents, and those eddy currents now dissipate and make joule heating. That joule heating will heat the water, cook the food. Very quickly it is cooked. Okay, so that is the reason why I was mentioning that when the technology comes to the kitchen, then only it becomes useful and then only it's popular. I hope you know this. If you don't know, then that's where the Maxwell's equations are actually. So this B and variation of electric field is trying to cook your food in the. So actually, after you go through those Maxwell's equations, those 4 equations, and talk about the speed of light, then only this sin I by sin r is equal to n, sin I is equal to sin r, the law of reflection, law of refraction, those equations you can actually prove by using these wave equations. Okay, so in electromagnetic. So this refractive index n, which was C by n in the previous class, the dielectric constant is actually relative permittivity, right? Epsilon r, epsilon by epsilon naught. Okay, and you know the dielectric which we are made of, one of the dielectrics, 75%. And some people mix some dielectric constant with other dielectric constant, then drink. You know the alcohol, what is the dielectric constant of that? No, water has 80. So if I say it's a dielectric constant of 80, the liquid, the chemical, and well, before drinking you have to think a moment, right? Isn't it? So similarly, so that dielectric constant K, 80, is actually 1 plus chi E. This you will definitely come across in your 10 plus 2. Yes, this is susceptibility, electrical susceptibility, and this is a dimensionless quantity. This is dimensionless quantity because it's a ratio, and therefore if you say what is the susceptibility of water, it will be about 79 because 80 is the dielectric constant. And this susceptibility becomes very important at some stage where you work later. The question here is that can we change the dielectric constant of any liquid or any material? If we can change, then we can change the susceptibility. Okay, so that question probably will not be answered, but we'll see. Yes, actually it is. What happens is so you have these. Do you know this? The polarization vector, I will explain, is number of dipoles per unit volume, and polarization is induced polarization. So you have any material, you put some external electric field, you will have the material polarized in plus and minus because the electric field will drive those plus charges that side. Actually the moving is done by electrons, so plus and minus. So inside also there will be one field. So the material is polarized. The induced polarization is proportional to the incident electric field. So if you put this, if you replace this proportionality sign, you start writing chi E into E. This is the susceptibility here. But if you, so there is a small thing remaining there, but they say it again. Yeah, the question is why? Why should the epsilon naught come here is the question. Okay. Epsilon naught will have dimensions because it comes in 1 by 4 pi epsilon naught q1 q2 by r square force. Therefore, to balance the dimensions of this and this, you start putting one epsilon naught here. So this is dimensionless quantity, constant, but you put one epsilon naught here. This epsilon naught comes for the balancing the units of P with the E. So that's where the chi-E comes. It's known as electrical susceptibility. Electrical susceptibility. There is a magnetic susceptibility also later. So similar equation would come. Magnetization is proportional to B or something, H or something. Yeah. So similar. You know, the Young's double slit experiment, which you must have already known by now, by name at least, if you haven't yet done this, but you know the Young's double slit experiment. Nobody has done it at home or in a school, but you know there are two small holes, you pass through the light and then they interfere, you get bright, dark, and the fringe width and the nth fringe, bright fringe, and distances you can find out. That tells the wave nature of light. Okay, so that's the more important related experiment is done by electrons to show their wave nature by Hitachi. Actually, the experiment was done by Hitachi by using the electron gun with two small holes and then putting on the detector here. The detector is moving. If these are the just particles, then you would get one peak here, one peak here. Okay, but because they are waves, you start getting the interference. That's also a well-known experiment. It's given in Feynman's book also. But Hitachi has done an experiment that you can Google it. Hitachi experiment. Hitachi, you know, right? A company which makes a lot of these materials. If you search that, you will get a video of that. When only two electrons go, then they only go at two places. When many electrons go, then they start actually making interference. But my aim was not to show this. Just to show that, do you know what is coherence, by the way? Okay, says sa. Repeat. Sa. Didn't come up. Sa. Repeat. Sa. No. Sa. No, that's again sa. No, it has to be sa. 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 So this first sa is the lower sa, but the other sa is the higher note, no? Sa, re, ga, ma, pa, dha, ni, sa, re. Okay. So when we were saying together, we were saying it coherently, right? We were saying, all of us were trying to add our phases, our frequencies of our throats as close as possible, right? So that's a coherent way of saying. Incoherent was when I was saying sa, you were saying sa. That's not coherent. So coherence means the phase. So if I can say amplitude and time, let us say, this is one wave, wave number 1, this is another wave, wave number 2. You would realize that if I keep on drawing like this, at some point of time, this and this would come opposite to each other. They would add up destructively. But up to a certain point, they will have some phase relationship. So when two frequencies or two wavelengths are going in phase, not exactly 100% in phase, but some phase relationship they keep. But they don't completely go out of phase. That means they are coherent. Okay? the two waves are coherent. So what I mean to say here is that I have some beam of light, and which is putting, so that beam of light, you can think this spot is that big, that spot is this big, okay, that green spot is this big. So that green spot, top portion and bottom portion, are they coherent? The one which is going from here, the one which is going from here, of course from here and here, is all parts of beam are giving same phase relationship is the question. So that is why my beam is coherent or not will be no. So I will have a coherence length. That means if I have some time up to which they are coherent, then speed of light will come into picture, because speed is velocity by distance or time, sorry, v is equal to s by t. So if you talk of t, you can talk of d, because the speed of light is given. So you can talk of coherence time or coherence length. Okay, so the coherence term is therefore very useful. Okay, so coherence of a light source is very, very useful term. So incoherent sources, their coherence lengths are very small. It's a relative term. It's a relative term. Okay, it can be highly coherent. An ideal light, ideal laser light, you can make an ideal light which are all lights coming out from this are coherent, all frequencies. Not always. Practically it is not possible, but they will be reasonably coherent. So now you know these are the Young's double slits. Now you can see the interferences. If you can see very bright interference up to which, that means they are coherent. If you can't see beyond something, then they are not, because this small s between the two sources will come into picture in the Young's double slit experiment. Therefore, by the way, some of these experiments, Young's double slit, those small experiments will not leave, the pendulum will not leave you for your lifetime. So better learn them now nicely. Okay, so very useful.
Sir.
So here we are talking spatial coherence. Here we talked about temporal coherence. Okay, you should have space as well. Temporal. Yes, there was some question.
Sir, could you repeat what coherent length means?
Say
coherent length.
Length. So velocity is equal to distance by time. So this is c for speed of light. If I am talking about the t, that means if my frequencies are up to certain time they are related, I can say, okay, the time corresponding to that distance is known as coherence distance, coherence length. So if you can define time, you can define length. We'll see, it's soon coming up. Equation known. Current at some point is equal to initial current and e to the power minus t by RC. So charge and discharge of a capacitor comes in the next semester or next year. Charge and discharge of a capacitor. What about the radioactive decay? That comes later. Any chemical kinetics? Any? Yeah? I see, not done. Okay. Yeah, better you know this. Yeah, okay. Somewhere the idea is that any parameter P and its time plot follows an exponential. So e to the power minus t by tau, where this tau is the 1 by e of this is tau, the amplitude. Okay, it's not a very extraordinary mathematics or something. So I thought maybe at least you know this, e to the power minus t by RC. This RC is R is the resistance, T is the capacitance, and RC is the time constant. Therefore, this argument has no dimensions. It has dimensions of time. Okay, so this is well known formula for charge and discharge of capacitors. So I wanted to tell you this. another similar equation, I is equal to I0 e to the power minus alpha L. So I said I is equal to I0. So this alpha is something 1 by L. Alpha has dimensions of 1 by L, centimeter inverse. L is length. So if I have this L, then this case intensity, because I am talking about the light. This is initial intensity.
Sir, could you just clarify coherence is supposed to be constructive or destructive interference?
No, from constructive or destructive fringes, you start knowing about the coherence. So that's the reason of, knowing whether it is coherent or not. The idea means if I make a screen, now I take the screen where my Young's double slit experiment is there. So I have bright center fringe, bright, in between there is dark, okay. So bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, dark fringe, like this. Now you will realize that it is not infinity. You start seeing a little bit less here, and then you don't see any fringe here. So if you have a good coherent source, you still see fringes. If you don't have, then, so that's another term known as visibility of the fringes. I maximum minus I minimum by I maximum plus I minimum, visibility or contrast, which tells you whether you see the fringes or not. So so that's the other way around, right? So destructive means dark, constructive means bright. That tells me about the coherence. So if you can appreciate those two, equations, then only we go further. Is it okay? So now I have some medium of length L having a alpha, and I have some wave I wanted to make it big, but it's too bad. So what will I get here? Anything changes here? This is T and this is amplitude. What will change? If my I is equal to I0 e to the power minus alpha L, it's because decaying, so finally it will be here, it will be less, right? Frequency won't change, so I'll have same thing here. So I will have something like this. So this is the loss by the system. Now if I change the equation, so this is the equation when I have I is equal to I0 e to the power minus alpha L. Suppose I have the equation which is I is equal to I0 e to the power plus alpha L. That means I put this from here, and if alpha is negative, because negative will become plus, so I need a negative alpha, it will become. So this was which was giving me loss. If I can somehow make the alpha, flip the sign of alpha, I start getting the amplification. So any word comes in the amplification to your mind? Light amplification, by stimulated emission, of radiation. So L A S E R, right? That you knew it. You wanted to show as if you don't know. Yes.
Sir, what exactly is alpha in the last formula that you gave us?
One question from here also. No, only that. What was the alpha?
What does alpha represent?
No, I said like a magician. I said alpha prime. Let us say here is equal to minus alpha.
So, but what is alpha?
Alpha is absorption coefficient here. I said no loss. I said you have a loss in the length L, so you get this. Till that you had no questions. Only thing is when I said this one, then you have start question. So then I said alpha prime, which was the new alpha here, is minus of the previous alpha. Then in that case, if I put this light from here, I would get the amplified light. And that seems to be the light amplification. That's the principle of lasers. How do you do it is a different question. I think we are soon coming back to the end of this thing. I don't know if you wanted more talk in this, we can have later, but so you know the idea was we do look, this is you see in the lab, you start seeing like the stars and then you see only single particle. Those are the particles of 30 micrometers. This is the distance. These are the micro bottles which are of 10 micrometers. So they are about few micrometers. Your hair, do you know what is your hair dimensions? Typically somebody will have very thick, somebody will have thin. Resham ke jaise baal, they say, no? How much? 100 micrometers. 100 microns is the hair which you can see. So you can't see the small one. So that's the microscopy. And anybody gone to Lucknow for this Imam Bada? There is Lucknow, you know, there is one this kind of thing. Or in Bijapur, there is this dome. This is some symmetric resonator in UK, in London, where Rayleigh was there in the Sunday. See, these religious people, they go to church, but they start doing science. So he was in church and sitting, but he saw that some sound is coming back from the around this resonator, but when he goes in the middle, that sound doesn't come. He goes to again there, sound comes from that side. He goes to the middle, that sound doesn't come. That chime, some chime. So he found, oh, I see, there is a kind of a mode, resonating some sound is there. He said these are the whispering gallery modes, something like that. So very famous. So that was an acoustic. But because we work in light, we started doing in light beams. Okay. So that kind of, we do some experiments like this. Now, because we have almost no time, I'll stop the lecture here. I have few demonstrations which will take some 30 seconds. So this was a one light laser. This is another laser which is blue. This is green. This is blue. This is green. Okay. Now I have this. You still see something there? Yeah. So that is phosphorescence, which remains for longer time. If I want to ask you to measure the lifetime of this, you can measure, because you put this and then start measuring your 1, 2, 3, 4, 5, 6 seconds. That t is equal to time, 1 by e of the time. It's a 1 by e is about half, 1.2.303. Okay, and then similarly I had made this sample. See, this is made in the laboratory here. That was Chinese, which was shown. This was here. Okay. So you can measure the lifetime. See how? So these lifetimes can be of seconds, hours, nanoseconds, microseconds, picoseconds, femtoseconds, invisible region. Okay, so those, as I said, the eye protein will have again lifetime about a nanosecond. So if you want to study that, you need this event to be very fast. Then to measure that. Wait, now another, for example, this wouldn't show that time delay. You see this immediately going on. Immediately when I give light, instantaneously it goes out. That time delay is not there. In that there was a time delay, right? So this is a fluorescence, not phosphorescence. Okay. Because I think I was just going into polarization and I didn't go there. So, these are the two polarizers. Polarizers generally, if you rotate the dark, you should see the dark, right? You rotate, you will see. But what are you seeing? Do you see some colors also there? You see colors? Okay. So you see dark. So these are polarizers, just parallel and perpendicular. Transmits, doesn't transmit. But if you put some tape on one of them, so the tape, randomly you just keep on pasting tape. Then tape also is a kind of a polarizer. These screens are also polarizing screens of computer, no? So you get one polarizer, you can see the dark. So this becomes kaleidoscope, no? What is that? So various colors. Yeah. So depending upon the thickness of there are tapes randomly pasted. So thickness of those layers are different. One thickness. So simple linear optics will explain this. These are the lambda by 2 plates, lambda by 4 plates and so on. Very simple examples of tape. I think we would close there. So when you come back to our IITs for doing some research, we will explain you all this plus alpha and minus alpha, how the laser and so on. Okay. Yes, one question here.
Yes, sir. When you were shining the laser light on the phosphorescent material, like the laser light, the regular color was kind of like a violetish blue, but when you were shining it on the material, it became blue in color.
Right. Yeah. So the idea is that I give some energy, IGNOU. I must get either the same energy. So I give blue. Blue is about 3 electron volts. Let's say I should get 3 electron volt, or there must be some, because there are finally atoms, molecules which vibrate, rotate, lose some energy. So my energy level should come little down. Then I should get less than 3 electron volts, which is smaller energy but red shifted. So blue excitation, I will get yellow or red emission. But there are other way around also, that you have to come for PhD.
Sir, then for example, if you shine red color light,
yeah,
will you get like if you shine red color light and it absorbs energy, so the returning light is infrared, you won't see anything. You'll just feel it'll just radiate as heat.
You say red?
Yes, sir. If you shine red light,
yes, shine, yes.
So that will get red shifted into infrared.
You obviously see, if you shine red, so you give some red light. If it is blue, then red will be somewhere here, let us say. Then you won't see this light, right? Infrared will have even zero, even lesser.
So it just become hot. Like you'll feel the heat.
Yeah, heat is always there. So heat is always there because you give some photons, there are agitations and vibrations, you start disturbing the system. So
one time when you showed the polarizer,
yes,
it was green in color, and the other time it was like purplish violet.
yes.
So how do you explain the phenomena of the different colors, sir?
Once I showed the green light, say it again.
So one time when you like changed the polarizer, it became green.
Oh,
And the other time it was purple. Did you?
yeah, no, not only green or purple, it has many colors. Near people could see, it's not only purple or green, it has all kind of colors. So all kind of colors you can get, because depending upon the thickness of the tape which is there. Yeah. Okay, I think that's all I would